Okay, I wanted to create a lecture to talk a little bit more about embedded implementation. We started talking about this, in class, but really I want to talk a little bit more detail into what's going on and also show you guys basically an example of actually implementing this particular system so you can see what's involved. So, implementing this in a microcontroller, there's definitely a lot of things to consider. It can be very confusing, when you try to do this. So I want to go through it and kind of show you guys what's involved. So, last time we talked about embedded implementation, we kind of started with this, or ended with this block diagram, where we basically have in the dot dash line is our microcontroller. So this is what we're actually putting kind of into code. And outside of that is the actual physical motor and driver, the physical encoder. So we kind of came up with maybe PI control is an appropriate controller for this type of situation. So right now that's kind of shown here just as a block in the Laplace domain, the typical continuous domain representation of a PI controller, right? So obviously, we talked about this in class, but this is something we don't necessarily want to implement in the continuous domain, and we can't because we're in a embedded controller that's in a discrete domain. We're going to be going through iterations. So it's really a discrete linear system that we want to implement, not a continuous system. So that's really what we're going to be going through in a little more detail today. So again, we kind of expanded that block diagram to show that this is kind of a Laplace representation of the controller, where actually this is kind of happening in the time domain or the discrete domain, but right now we're just kind of representing it as a PI controller in the Laplace domain. So we have the error signal coming in and the controller output coming out, which is what we're calling our P, which is, you know, you can think of it as a representation of the duty cycle, maybe between 0 and 1. Depending how you implement that in the embedded controller, that could be the pulse value. It could be, a kind of a normalized value from 0 to 1, which represents pulse. It really just kind of depends on how you implement it, and there's several options. Um, I think in general, I like to make P in this case kind of equal to the RPMs I'm trying to get. So, and then you would have to kind of convert that to, use a conversion from RPMs to pulse value, which you can do just by, putting in a 50% duty cycle and seeing what RPMs you get out, open loop, or that's kind of a good general way to do it. Kind of like, what was done in the lab for 5314. If you're in that class, we looked at the actual motor RPM per different duty cycles. And that's not really a direct linear curve, because the motor's not going to start turning, at 1% duty cycle. You kind of have to give it to a certain point. So, but for the purposes of this, it's you just need something that gets it close. If you have a closed loop system, it's going to actually close that loop, and it's going to make the encoder measured RPM, equal your command. But if you don't get that close, that conversion close, it'll add some gain factor or something to your actual system, and your response could be a little bit different than you expect. Um, okay, so we talked about implementing this controller D in terms of maybe the Z transform instead of the S transform. Obviously, we need to have some sort of discrete representation of that instead of a continuous representation. And in class we talked about how we can use this forward Euler discretization model. There's also a backward one, which is kind of what we'll actually be transforming this into. But in that case, the s variable is replaced with z minus 1 over ts. So what is that really? If you think about that, z is like a delay. So z to the plus 1 would be the next element. So really it's saying, if you were to look at this transfer function, you're basically saying you know, a sample minus its delayed, you know, its delayed version. In other words, two consecutive samples divided by the sample time. So really, what is it? That's the derivative, right? So if you think of the approximation of a derivative, you take the difference of two samples and divide by that time, and you're kind of getting a, you know, a dy by dt or something like that, if you will. So, you know, whether you write this in terms of z or z inverse, it's still kind of the same thing. This could be, if you multiply this by z inverse over z inverse, then you get something more like what we'd express in a causal system. But we can, you know, use this right now just to keep things clean, and then at the very end convert to z inverse before we form the actual difference equation. But I just want to mention that because we didn't really talk about that in class, where this comes from. You know, this Euler discretization model is really just estimating the derivative, right? S in the Laplace domain represents a derivative. And in the z domain, that can be kind of thought of as the difference of two samples divided by the sample time, right? So d by dt of some continuous value can be estimated that way. So if we take our ds, which is kp plus ki 1 over s, and we use this transformation, then you get basically something that looks like this, right? So we replaced this s here with z minus 1 over ts, and then now we're basically combining these fractions, so it becomes kp times z minus 1 plus kits over z minus 1. So that's the z transform, the z equivalent of this Laplace PI controller. Okay, so we want to convert this to something in terms of kind of z inverse, because we're going to be looking at, you know, looking at delayed samples instead of future samples. This is, you know, going to be something that's more of a causal system. So we can just multiply that z transform polynomial ratio by z inverse over z inverse. And if we do that, we get, you know, kp times 1 minus z inverse plus kits times z inverse over 1 minus z inverse. Of course, that's equal to p of z over e of z. So for, you know, the process for converting this to a difference equation, we need to cross multiply. So we get p of z times the denominator is e of z times the numerator. And now we can use our z transform properties, namely the shifting property, which means if you have like pz times z inverse, the inverse z transform of that would be p of n minus 1. So in this case, p of z times 1, transform that to pn, and then minus pn minus 1. Then you can see we have ez times all these factors, so we're going to have kp times en minus e of n minus 1, comes from multiplying ez by these two, right? And then plus, you have ez times kits z minus 1, so that becomes kits e of n minus 1. Okay, and then the next step, we're just basically solving for p of n. So this is our output of our controller, given the previous output of the controller, plus kp times basically our the difference in the error from this iteration and the last iteration, and then plus kits times the previous error. So this is really the difference equation that we're going to implement in the controller. So for this, it's a, you know, it's a first order system, so we're really only having to retain one historical value. So we'll have a variable for, you know, the previous controller output. We'll have another variable for the previous error, so that we can, you know, implement this difference equation iteratively using, you know, current error, previous error, and previous output, and then we can find the current control output, okay, for a certain error signal. So, you know, just to verify that this difference equation really is representing our desired PI controller, we can, you know, divide everything by t sub s, and we get this form down here, which should start looking like something that is um, closer to what we're trying to do in the S domain, right? Okay, so if we look at this, if you're looking at the difference of two samples divided by the time, remember what we talked about, that is really an estimate of the derivative, right? So this difference equation, when you divide by TS, you see basically you have, this is kind of an estimate of the derivative of P, and you have Kp times the estimate of the derivative of E, and then plus Ki times the error, right? So if we kind of write that back in terms of like the equivalent of a continuous system, this is the derivative of P, so we could write that as P dot. This is the derivative of E, so write that as E dot. And of course this is E. So you put that in time domain, convert that to Laplace, so the P dot becomes SP, E dot becomes SE, and so on. And then we can basically write that in terms of P over E. If you do that, you get this, which simplifies to Kp plus Ki 1 over S. So really just another quick check just to show that, yeah, these systems are equivalent. This is the Laplace domain, this is the discrete domain, but the behavior of these should be very similar if we are iterating fast enough, right? Because you need to make sure that these samples are close enough together relative to the bandwidth of your system so that this derivative estimation is accurate. So obviously if you're looking at samples that are seconds apart in our system, that derivative is not going to be very accurate. So the whole this difference equation is really contingent on your sample rate or your simulation time being fast enough relative to the bandwidth of your system so that this derivative is accurate. So that's kind of getting into the realm of you need to sample your simulation at the Nyquist rate, which would be twice the bandwidth of your system. So we didn't really talk too much about the bandwidth of the system in this case, but for the purposes of this course, we'll probably just kind of feel that out. If if you're looking at something that has a rise time in about a second, you're going to need to sample that probably 100 times per second or something like that to really get these samples close together so that they really estimate that derivative. You could probably relax that somewhat, but you kind of want to be careful with that. Okay, so this basically verifies that this difference equation that we can implement in the microcontroller, theoretically is the same thing as our continuous domain PI controller. And the faster you iterate, or the smaller the smaller TS gets, then that will equal. They'll be equal, right? So as long as TS is sufficiently small, then these should be approximately the same thing. Okay, so now instead of a Laplace representation of that controller in our microcontroller, which we can't really implement, now we have something we can implement in the discrete domain. So if we write out that difference equation, again, this is what that looks like. And this should be able to, this will let us calculate that PWM signal or duty cycle or pulse value, whatever you want that to represent, from the error signal, which is derived from our command minus our actual RPM. Okay, so now everything in the dashed line here is in discrete form, so we can actually implement that directly, and that's what we're going to do. Okay, so before we do that, I think it's convenient to do like a little MATLAB simulation. MATLAB can be used like a discrete embedded system, right? We can iterate, we can use for loops, so we can kind of test out the iteration. Before we kind of looked at the closed loop of this entire system, the controller and the motor and driver. That's what was used to kind of derive the parameters for our controller. So we know we can do that, but what about simulating this controller separately from the motor and driver? That can be a little bit insightful, I think, to actually see what this P signal looks like instead of looking at just the entire closed loop output, given a command input. So the MATLAB simulation, we're going to implement the controller by itself, get this P of N signal, and then we're going to use that to drive the response of the motor and driver. And we can do that using state space variables. So it's basically forming a time domain simulation, which is really kind of what we're doing in our embedded controller, right? This is going to be an iterative time domain implementation, so we can kind of implement that the same way in MATLAB and make sure that everything looks good. So we can basically do that, and then we can also compare to the closed loop response of the total system, and those should be pretty close, right? If there's something not the same, then obviously we need to look and see if there's something wrong in our implementation. But it's kind of a second data point, give us a good feeling that the way we're implementing things is going to work. Also, that gives us an opportunity, if we want to, maybe put some non-linear constraints on some of these values, like if you wanted to, for instance, P, the duty cycle, in the time domain simulation with no other constraints, P could be any value, right? It could go above 1, it could go below 0. But if we're meaning that to be the duty cycle or the pulse value, we can put some constraints on that in the simulation if we want to see what impact that's going to have on the control system. Because, ideally, P might want to swing really wide, right? It might want to go really, really high, but in actuality, the pulse, can't go over 100%. So if our ARR is 9999, that's really that's the practical limit of our pulse value. Anything above that is not going to create, a higher voltage for the motor. The 0 to 100% duty cycle is really going to be the limits for what's going to actually change our motor. So we could implement nonlinearities and things like that in the simulation if we wanted to see how that might impact, the embedded implementation that will also have those nonlinear constraints. Okay, so the approach here will be use the difference equation that we just derived to simulate the controller, generate that P sub n output, and then we can run that into the state space simulation of the physical motor and driver, which we've already looked at. And instead of using just a command for that for the step response, we'll be using this controller output, and that should give us the predicted time domain response of the combined controller and the physical system. Okay. So if we do that, and I can share this MATLAB simulation with you guys, we're basically simulating this PI control, so we're simulating this difference equation. If we do that, we can do that a couple different ways. We can look at the embedded simulation where we're using the controller, and an embedded simulation where we're not using the controller and just using the command as an input to the motor. And here you get these two different responses. So for these particular PI parameters, we get a pretty good response. A little bit overshoot here just as an example response. We could always tweak these numbers and probably tune this up a little bit better, but the key here is that in the time domain simulation in MATLAB, our response is equal to when we look at the entire Laplace domain closed loop step response. So to me, this tells me that our embedded discrete implementation of that controller is going to give us our predicted time domain response. So I won't look over the MATLAB in this lecture, but we certainly can take a look at that in class. And it's basically just implementing this difference equation. It's a for loop where we initialize everything to 0. We implement this difference equation to give us P as a function of that error. We calculate the error as the command minus the actual RPM, and then after this we go into the state space simulation like we did before. Okay, so this just kind of gives us a good feeling that our implementation and our representation of everything here in the discrete domain is going to actually be what we expect. Okay, so as another example, let's look at doing the same thing for maybe a PID controller. So I just created an example system here. Doesn't really have a physical representation. This is just a pure, like a mathematical type simulation. So created this system. It's a second order system. You can see just by looking at this, if at s goes to 0, in other words, when t goes to infinity, you can see that this kind of goes to 5/10. So the step response of this is going to end up at about a half. So you could never get to 1, so you could put a command of 1 in, and then this is going to settle basically at 5/10, which is 1/2. So this would be a good system that might benefit from a PID controller. Maybe PI controller would be just fine as well, but I kind of want to show the implementation of a PID controller. Okay, so again, we're going to use the controllable canonical form. So we're going to kind of multiply this by z of s over z of s. That gives us the numerator. Y of s is z dot plus 5z, and the input is z double dot plus 2z dot plus 10z. Then we can define our state space variables. X1 is z, x2 is z dot. So we can write those in terms of the others, write the state space variable derivatives in terms of themselves. And we get x1 dot, which is basically z dot, which is x2. And then we get x2 dot, which is going to be z double dot, which we can look up here is going to be u minus 2z dot, which is x2, right? So minus 2x2, and then minus 10z, which is 10 times x1. So now we have our state space variables and representation here, and just keep in mind that now the output is equal to z dot plus 5z, which is equal to x2 plus 5x1. Okay, so again, something that we can easily implement in the embedded system or in a iterative environment to calculate this system's step response or response to any input, right? We can have the state space representation of that, which we have done before in the past. Okay, so again, we're implementing this by estimating these integrals, right? So x1 would be the integral of x2, and x2 would be the integral of this right here. So that's how we've simulated proper transfer functions before. Okay. All right, so when we do that, implement that, we have this controller here, kp plus ki 1 over s plus skd, multiplying by s squared over, multiplying by, basically combining this into one fraction. You get kds squared plus kps plus ki all over s. If we convert that to a differential equation, we basically get p dot, that's from the SPS on the left, and then we have e times this polynomial here, which gives us kd e double dot plus kp e dot plus ki times e. Okay, so we can basically use that conversion from s to z, or we can just kind of go directly from what we know about how that works and say, well, p dot we can estimate as this, right? Previous consecutive samples difference divided by ts. E double dot, gets a little tricky. Think of this as e dot and this is the previous e dot, right? So we're looking at the difference of the differences. So this is kind of how we can use previous 3 samples, or the current and the previous 2 samples, to estimate the actual second derivative. Okay, so hopefully that makes sense. This is going to be, e dot, and this is going to be e dot of I minus 1, if that makes sense. Okay, and then this is just estimating e dot, and then this is ki times the error itself. Okay, so this is what we can use to form our difference equation. We multiply by ts and move this pi minus 1 on the other side. We get this difference equation down here at the bottom for our PID controller. Okay, and if we perform the simulation, you can see that now the output of our controller is a blue line. Now for a step function, we are getting something that kind of converges up here to our desired 1. So you can see, there's kind of there's an oscillation that's kind of given by our proportional, maybe a little bit of our derivative, but that ki factor is kind of causing an error based on, the fact that we're not equal to 1. So that kind of takes over as time goes forward, and the impact of KP and KD are reduced as we kind of settle. That KI factor takes over and creates enough error signals so that we get steered up to this desired value of 1. So again, the open loop without the controller would settle at about 0.5 because of that transfer function. Okay, so again, here we can do a time domain simulation, and then we can also just do a step response, and you can see that they do appear to be equal or very close. So again, this would tell me that for the iteration time we have here, which I'm using 0.001 for both of these simulations, which may not be what we use in the controller, but you could use this in the controller or something similar. We're just showing that, yeah, those derivatives look like they are being estimated correctly because these responses do look equivalent. Okay, some notes on embedded implementation simulation speed. This is kind of the iteration rate we've been talking about. This must be sufficiently fast to handle the bandwidth of the system. So you need to make sure that the iteration time or the sampling time is at the Nyquist rate or higher, twice the highest bandwidth of your system. So in general, you could look at what is the bandwidth of your system by looking at the the frequency response, and then make sure you sample twice that. So care must be taken in this embedded implementation to make sure that you have a consistent time base. You don't want the iteration time to be changing. Okay, so we don't want to just go in our while loop, infinite while loop, and just do a bunch of calculations, because that that time base might be changing depending on the size of all these numbers that you're multiplying to calculate the controller. The actual operation or calculation time might be varying. So that's why we're going to use a timer to get a consistent time base that we know is predictable, give us a consistent T sub s that we can use in our calculations, and that we're not going to exceed in our calculation time. So what I like to do is output to the console what that calculation time is. So within for all these calculations for the controller and the simulation, I like to start kind of get a time delta for that, and just make sure that that calculation time, that processing time for all the code is going to be significantly less than the iteration rate. So if you're iterating at 100 times a second, in other words 0.01 seconds per iteration, you'd want your calculations to be less than maybe a tenth of that, right? So maybe 0.001. You'd want all the calculations to be done maybe in a millisecond. It can get right up to it, but just keep in mind there's going to be some variation in that time, so you want to leave a little bit of a buffer there. So I'll show how we can do that in the code. And also something to think about is some peripherals may limit that iteration rate. So you could have a lot of different kind of peripherals in your system. You could have A to Ds or different things that are sampling. In our application, what we'll find is that the timer that we're using for encoder mode is only really calculating encoder counts at a certain rate. And that rate is going to be dependent on, kind of how often pulses are coming in from the encoder. So if we sample that too fast, we'll see that the timer hasn't had sufficient time to actually process those pulses coming in. So in that case, we'll get some erroneous results. So for this implementation, we'll find that the encoder is kind of the limiting factor to how fast we can actually perform this simulation. Okay, so that's something that we need to think about, is all the peripherals that are involved. You want to make sure they can operate, faster than our simulation rate. So all these factors kind of come in to have you choose an actual simulation rate. As it turns out, for this implementation, we're going to do a simulation rate of basically 10 milliseconds or 100 times per second. That's kind of the limit for what we can do with that encoder. If we try to start getting down to more like a millisecond, then that encoder, the output of that encoder is not going to give us good results. In other words, we might read it and consecutive readings might give us the same value because it hasn't had time to process additional pulses. And so that's going to tell us when we look at the difference of those counts, it's going to be 0, and the simulation is going to think that there is, basically 0 change in angle and a 0 rate. So even though there's a small change in angle and maybe a small change in rate, that processing time hasn't happened yet. So having that 0 in there can really cause some issues in the implementation. Okay. So here's the approach we're going to take to implementing this. We're going to use timers 1 and 2 for encoder and PWM mode. So, we need to read the encoder from the motor, and we need to use a PWM mode to actually control the duty cycle going into the driver. So we'll use those 2 timers. We also need another timer just to control the iteration speed of our simulation. So we'll just use a basic timer or one of the available timers in basic timer mode just to give us a consistent interrupt at about 100 milliseconds. Okay, and all the processing for this control system will occur inside the callback function for that timer. So every time that timer hits the ARR value, every 10 milliseconds, it's going to run this callback function, and we can calculate all these parameters for our control system. As an example, I'm just going to use a command that's toggling between 100 and 200 RPMs. So that'll just show us kind of like a square wave as an input, just so we can consistently see the response as this thing goes up and down. It's just a good way to show kind of a continuous version of the step response. So picked 100 and 200 RPMs, not just as an example. You can use whatever you want for that. So we'll need a 4th timer, basically operating at around 1 toggle every 2 seconds or so. So 4 timers overall that we'll need to implement for this. You could, if you wanted to slow down the printf of these parameters, you could have a 5th timer, but what I found in this one is there's plenty of processing power to actually have that printf come out at the simulation rate. So sometimes you might need to slow that down if you're simulating something very, very quickly. The printf can be something that'll really slow you down. In this case, there's enough processing power. Okay, so we're also going to include our simulated time domain response from that MATLAB simulation. So we kind of got a time domain simulation from MATLAB. We're going to implement that in the microcontroller as well, just so we can have something to compare to. So if we, send that output out with the calculated, measured RPM of the motor, that tells us if we're kind of on track with everything. Those should look relatively similar, right? They should have, if we modeled our motor correctly, then the RPM of the motor should look like our simulated RPM of the motor. So we can implement that simulation inside our microcontroller just to have something to compare to. So we'll use USART2 to send data to the serial port. Serial port plotter. That way we can get some real-time plots of what the motor RPM is doing, what these simulated time domain responses look like, etc. Look at all the parameters. And we'll also look at this motor response with and without the controller. So if we just take our simulated, or if we just take our p-value, if we use our p-value controlling the PWM, then that's going to be, basically closing the loop of our control system. But if we just want to look at the, step response of just the motor and the driver, we can just use the actual command, this 100 to 200 RPM. We can just output that in PWM, and that'll give us, our motor step response without any control. So we'll look at it a couple different ways so that we can you just get a good feeling, make sure we've got the motor modeled correctly, make sure everything kind of lines up. Okay, so let's go to the IDE and let's start thinking about how we can code this up. Okay, so we're in our IDE here. Start a new project. Okay. Okay, I'm going to call this motor controller. Okay, and we'll leave all this default. And I'm going to say no here. Remember, it's very important to say no here, unless you want to do some, you know, use a higher clock rate or things like that. And, you know, we're going to use the some default values for the timer. I mean the clock configuration. Let's see. I'm going to go ahead and click on this HSI switch here. So we're going to use basically a APB1 timer clock value of 8 megahertz. Okay, that's going to make things a little bit easier to calculate when we start calculating some of these timer values. Okay, so just click that button right there, and then that should put this. It should be using this 16 megahertz with these parameters here, which kind of divides that down to 8 megahertz for all the timers that we'll be using for this. Okay. All right. So we go to the configuration. We're definitely going to want timer 1. Timer 1 we're going to use in, let's see, I think that would be encoder mode, right? Yes. So number 1 we will use in encoder mode. Okay. And we'll leave everything else default there, I believe. Timer 2 we're going to use in PWM generation mode for channel 1. That's going to come out on PA15. And we'll leave, well, we need to set some settings for that, right? So I'm going to put a prescaler here of 2, and I'm going to put a period of 9999. Okay, so that's going to, this is our ARR, so our this will give us a, this is our ARR, so our pulse value will be a percentage of this, right? So 0 to 10,000 essentially will give us our PWM duty cycle from 0 to 100%. Okay. I'm also going to use timer 3. Let's use this. Let's see, do we use timer 3? Let's see. Okay, timer 3. We're not going to use timer 3. So timer 3 could be if you want to change, you know, maybe the rate of your printing. So we're going to use timer 7, and that's going to be our simulation time. So let's go to 7. We're going to activate that. So this is going to be what we're going to set to about 100 times a second, or 10 milliseconds. So this is an 8 megahertz clock on this timer, right? This APB1 is 8 megahertz. So if we wanted to calculate some values for that, we would say, 8 megahertz, and I'm going to maybe divide that down by 4,000. So 4,000 gives us 2,000. So if we wanted to have this go at 100 times a second, then we'd need basically a period of 19, right? So dividing that by 20 will give us our 100 per second. Okay. All right. So this could be 39.99, and this could be 19. That sounds right. Let me double check over here. Make sure that looks right. For timer 7. Yeah, that can work. Yeah, I think that should work. Double checking here. Okay. All right, so that is timer 1, 2, and 7. And I'm going to have one more timer that we can use just to have running in the background to use as a time reference. So if we want to calculate the processing time for some of these, I'm going to use timer 4 for that. So for timer 4, I'm just going to use the basic timer mode of that, right? So for that, I want it to run as fast as it runs, and I'll just look at consecutive counts and calculate, what that is. So, some of these are already used up, these channels. Just pick an available channel, and you can say, output compared no output. That'll basically let this just operate as a basic timer. Some parameters, I want this to run as fast as it can, so no prescale, and I'll have the counter period at the maximum. So it's a 16-bit value, so that's the maximum of the counter period. So this will be counting very, very, very quickly, so we can grab counts at different times. We can subtract those, and knowing the clock count rate of this timer, we can actually convert that to time. Okay, so basically using 4 timers here: PWM mode, encoder mode, a simulation time, and then just a general clock, just so we can actually calculate processing times. Okay, we'll also need USART2. So under connectivity, I'm going to go to USART2, put that in asynchronous mode. Okay, so let's think about interrupts. For timer 7, we definitely want to make sure we have the interrupt enabled, right? That's going to be our simulation time. Oh, we need one more timer for toggling the input, right? Okay, so we'll use timer 6 for that. So we'll activate timer 6. We'll want an interrupt for that. So click the enable the interrupt, parameter settings. We want this to be every couple seconds. So let's say we take a prescaler of 39.99. So that's going to go 2,000 times a second, and we're going to maybe use a period of 29.99. So maybe that's like a second and a half per toggle, something like that. So this is just the rate at which our input is going to be changing. So that could be whatever you want it to be, but that seems to be like a good reasonable value. Okay, so actually implementing here 5 timers. We've got the UART enabled, so we should be good. Let's generate code. So the first thing we can do is implement our command toggle and just kind of look at that on the serial output and make sure that looks reasonable. Okay, so that would be timer 6, right? So let's go into here and say how timer, oops. We want the API for starting the timer. So that's going to be how time base. Yeah, sometimes it doesn't come up with that by default. So you can go into the driver if you want to find that actual API. I'm going to start this in IT mode. I don't know why it's not suggesting things. So we're going to start timer 6. Okay, so we have H timer 6 here. Okay, giving us a syntax error. Don't know why. It's not happy about something, is it? Oh, I think I know what's going on. Let's try this. We'll pause for a second so I can figure this out. Alright, so that was pretty easy to figure out. I was trying to do it up here in this global space instead of down here in main and after the timer had been initialized. So let's start timer 6. How timer base. Okay, we're going to start this timer in IT mode, and we're going to start timer 6. Okay, so we can start the others as we kind of implement those. So we need to come down here and add that callback function. So let's go to the driver, look for the callback function. We're just going to use the period elapsed callback, right? So Control F, find, and here we go. Oh, get to grab that. Okay, we grabbed our callback function. Implement that here. Okay, so here's our general callback. So for H timer 6, we want to make sure that we process if each time equals that, then we'll process this. Okay, so here we're going to toggle an input. I'm going to call it the value command. So the state, I'm going to toggle a state basically. So let's call that input. Let's go down to our let's go down to private variables. Let's say uint 8t. We'll call that input, and we'll make it. So this will be a 0 or a 1, basically toggling different commands we're going to give it, right? Okay, so we'll start with that being equal to 0. Let's go ahead and create a command for an RPM value. So let's make that float command, and we'll go ahead and say that's going to be equal to, I don't know, we can say that's equal to 0 to start. Okay, So in our callback function, this is going to be where we toggle that. So that's pretty easy to code. If input equals 0, then we'll say our RPM command equals 200, and then we'll change input equals 1. Okay, and then we'll do else command equals 100. So this will let us toggle between 100 and 200, and here we'll say input equals 0. So just, you know, that way we can go in here and change this command to toggle between whatever two values we want. Okay. All right, so let's, we need to get our printf functionality going so we can print that to the console. So I'm going to put in the put care functionality up here above it. So we can send UART2 to the, or sorry, send printf to the UART, and let's just, in this callback function, let's implement another one. Let's call it, let's do the one for simulation time. So that's going to be timer 7, right? This will be our simulation code section, right? So we could, you know. So in this case, we're not really processing. Let's just print the value of command to the console. So we're going to print to that serial plotter, so we need to use a $, and then print the float value, and semicolon, and then, okay, and of course we're going to get our little error, so we have to go to our project here and enable the printf with float. Okay. Okay. So let's get an error here. Let's fix that. Oh. Do that, and then here we're going to put command. Okay, so this timer 7 is going to be operating at 100 or 10 milliseconds. Let's see what do we have now. Oh, we need to include standard I/O up here. Okay. So in this case, you know, we'll print the value of command to the UART. We can plot that using the plotter just to kind of show that that is toggling at a reasonable rate. Okay. So let's plug in my microcontroller. Let's run this. Bring up the serial plotter. Okay, nothing's coming out of the UART for some reason. So let me figure out what's going on there. Oh, yep. So we have our UART2 initialized. Timer 6. Let's make sure we have the interrupt processing for timer 6 and 7. So we can go to our it.c. We do have 6 and 7 here. And we have timer 6 and 7 interrupt handlers. Okay, so that's good. Oh, we need to start timer 7, I think is the problem. Common mistake that I get all the time is, you know, you set up all these timers, but you have to actually start them before they'll work. Hal timer base start in IT mode, timer 7. Okay. Let's try that. Okay, now we're getting data. So let's change this to a minimum of 0 and a maximum of 300. And there you can see we have a toggling here of our input signal. Okay. All right, so that'll be the command. So we'll see kind of a response on top of that when we actually get everything implemented. We'll see the motor, you know, hopefully, you know, reaching these values as we command them. Okay. So let's go ahead and add our simulations so we can kind of look at those and make sure those are okay. Well, let's look at let's implement our encoder. Our encoder counts. So we've done this before. So in this simulation executable section, remember we need to, so I'm just going to copy and paste some stuff in here just for expediency. Where we're basically reading the encoder counts. That out for now. Okay, so we're getting encoder counts, converting that to an angle, finding this difference of angle, a change in angle, and then using some of our simulation parameters here and calculating the rate. So this will give us the angular rate in RPMs. So we need a simulation time in here. So let's go up to our variables and do float ts equals 0.01, right? That's our simulation time that we set for our timer. Okay, and just to make sure that's working, well, let's well, we'll look at that in just a minute after we get the well, we have a, let's see, let's set a pulse value here. And I'm just going to say pulse equals, you know, about 5,000. So that should give us a 50% duty cycle. So let's go ahead and make that a variable. Pulse, let's say it's uint 32. And we'll just make that initial value of 5,000 just to give it a initialization. Okay. All right, so we're using this HAL timer set compare. This is going to set the PWM percentage. So remember that was out of 9999. So this will just kind of give us an initial 50% duty cycle for that motor. Okay, and so now in addition to command, We'll also look at this rate that we're calculating. Okay. So let's compile this. Oh, some errors. Oh, got some variables we have to declare up here. So we've got count, which is going to be int 32. Oh no, it's going to be signed. So int 32t count. We've also got those angle values. So let's say float temp 1 and temp 2. Okay, float angle and rate. Does that cover everything? Oh, we've still got an issue down here. Let's check it out. Angle, oh, encoder counts. So this is some similar to what we did before. So this is equal to 750. That's basically how many. That's the resolution of the encoder. So that's how we calculate rate. We've done that before, so I'm not going to get too deep into that. Okay, what do we have now? What's the problem? Oh, too many arguments. So let's do rate will also be a float. Okay. Okay, so that looks good. I'm going to plug in the motor here. And let's run this and see what we have. Okay. Didn't work for some reason. So it's showing us the command, but it's showing us 0 RPMs, and the motor is definitely not turning right now. So let's see what we could be doing here. We set the compare the pulse of 49.99. Let's go back to that timer, just make sure that's the AR. Which timer was that? Timer 1. That's encoder. Timer 2. Period of 99.99. Okay. Maybe we need to start those timers. The same problem that we had before. Okay. Start those. I'll go ahead and start on both. Not using interrupts for these, right? Oh, and timer 1 is in encoder mode, right? So let's do this. Encoder start for timer 1, channel 1. Right. Okay, and we're going to start the PWM as well. That's timer 2. So we'll go to timer PWM start. That's going to be timer 2, and that's going to be channel 1 as well. Okay. We've got those 4 timers started. So let's run this again. Let's see what we have here. Okay. So now we have our command still kind of going in the background. We have our motor commanded to a 50% duty cycle, and you can see it's, you know, somewhere around 180 RPMs. So that tells me that the rate calculation is reasonable, right? I think we noticed open loop, these are somewhere around, you know, 240 or something like that. 50% duty cycle, they might be around, you know, 180, something like that. You know, one thing you'll notice is one problem you can have with this rate calculation is when that timer rolls over, you got to make sure you account for that, so you don't have a, you know, like a negative rate or something incorrect due to that timer rollover. So you also notice this is a very noisy signal. It's, you know, the timer, the encoder is not the highest quality on the motor, so you can see there is some kind of dither between values. So just expect that's going to be what that output is going to look like for the RPM of the motor. It's going to be kind of noisy, and that will impact our control system. So here you can see there's kind of a dropout value there. I'm not sure if that's happening due to the rollover of that timer. So what we can do is, let's look in that value next time it happens and see, you know, what it is. It's probably giving us a large negative number. So we auto scale, yeah, it's giving us a very large -65536 or something like that. So let's just put in a little bit of code just to prevent that, because if we enter that into our control system for that rate, it's going to be like a huge impulse. It's going to cause a lot of problems. So the way I would address that is to just kind of test that rate, and if the rate is less than 0, then we'll make it equal to the previous value. Otherwise, we'll set this temporary rate, you know, to the current. So that way, if it's ever less than 0, it's just going to use the previous value instead. If we do that, we should stop seeing those values. So we need to go make that a variable. So let's say is that what it was? Okay, rate and rate old. Okay, so we're putting out oh, looks like we're still getting, oh, we didn't compile it again. Okay. All right, so we're calculating the rate. So that's going to be one thing we're going to use as the input to our system, right? We need to compare the rate and the command, and that's going to be our error signal. Okay. So now we can say, we can calculate our error is going to be whatever the command is minus the rate. Okay. So we need to generate another variable up here called error. Okay. So that's the error that's going to be the input to our control system. Okay. So now we can actually, once we have the error, we can actually calculate the PI controller response, right? So remember, that is going to be that difference equation that we looked at before for a PI controller. So if we go back to our PI implementation, we have this difference equation here, right? Okay. So we'll need some new variables. We need to actually, you know, have some variables for our control system parameters. We need to, you know, define P. We already have error defined, so let's go ahead and look at float error P. What do we use as an example here? I'm going to use 2 as an example. I'll use 0.08 just to give some values there. Okay, so that's parameters of our actual, oh, sorry, that's motor parameters, so we don't need that yet. This is going to be Ki, make that 31. Okay, so let's do our controller output. So in this case we have P, according to that difference equation, P is going to be equal to P old, so we need another variable for P old, and error old, right? It's going to hold the previous values. So P is, this is the difference equation implementation. P equals P old plus proportional times the error difference, right? So error minus error old, and then plus our time simulation times Ki times error old. Okay, so that's our P value. Which was from that difference equation, right? It's really implementing this right here. Okay, so that's going to be the P value. So we have an error now. We have the error is the input to the controller, and this one line really is our, our controller, right? So that's going to generate P, which is going to be some value that we can map to a pulse value. Okay, so let's go ahead and use that to set the pulse. We'll calculate the pulse value, and we already defined that, so we can take this out since we're not going to be setting that manually. And here we'll say we want this to be unsigned integer. That's going to be, do the calculation in float of 10,000 10,000 counts times P. So if P is a if P is a value between 0 and 1, then that's going to give us, 0 counts or 0 duty cycle for P equals 0, and for P equals 1, that'll give us the full duty cycle. One thing to notice here, though, is this error is really in terms of RPM, right? Not a 0 to 1. So you really have to kind of consider what domain you want to be doing all of these calculations in. Do you want to kind of normalize it from 0 to 1, or do you want to have everything in terms of RPM? So lots of ways you can do it. I'm going to do it one way here, but you're welcome to kind of try different ways. In this case, I'm going to kind of make this error normalized. So I'm going to make it kind of something that is between, relative to kg, which is, remember, that parameter of the motor that we defined, which is kind of your open loop max rate of the motor. Let's call that, in this case, let's say that's 290. So let's say, just as an example, if that's when you have a 100% duty cycle, if that's the RPMs of your motor. Then we also, while we're at it, let's put in the TM value for our motor. So these are the two parameters that kind of define that open loop motor response. So you may have something different depending on your motor, or depending on you're matching the data for that model identification. Okay, so I'm going to make this error basically something that's more normalized. So instead of being an RPM, this kg is kind of a conversion between percentage duty cycle and RPM. So this would basically make this a kind of a percentage error, if you will. So that way P is now going to be in percentage error, and that way percentage of duty cycle. So now when we multiply that by 10,000, this pulse will be something between you know, 0 and 10,000 basically. And we can make this 999 if we want to be, you know, probably more appropriate. And then from there we'll set the pulse value of the motor. Okay, so that should actually close the loop on our motor control, right? So what do we want to print here? Let's print command and the rate. We can print P to see what that looks like. And let's go ahead and print the error too. So error and P are going to be kind of in percentage. So between 0 and 1. The command and the actual rate of that we calculate of the motor spinning are going to be in RPM. So, you know, these variables are going to be kind of in different ranges. So we need to keep that in mind if we want to plot those. Plotting those together isn't going to be super helpful, but okay. And let's compile. So we've got these are all floats, I believe. Okay, and then up here we have KP times that, not a function. And looks like we're good. Okay, so theoretically this should make the motor respond according to our PI controller, right? So let's see what happens. I'm going to restart serial plotter. And let's play. And let's change this scale from 0 to 250. Okay, so our command is going 1 to 200. And we can actually see our motor is actually working pretty well, but it's going from 75 to 150. So we need to figure out kind of what's going on there. We have our P and our error down here between 0 and 1. So if we change our scale from 0 to 1, we should see those. So error is, yeah, this orange. So that is showing the kind of the percentage error of our motor. And P is this gray signal, which you can see it's this is kind of what the control system is doing, right? It's trying to make that response go really fast, so it's causing the motor rise time to really crank up with this overshoot, right? And then causing the motor to kind of converge on that value. So we're pretty close on this. Let's go back to this and let's try to figure out why our motor is closing the loop at different values here. So if we look down here at the text, you can see it's kind of going between 80, 75 and 140 something, right? So not quite reaching our desired closed loop. So let's see if we can figure out what's going on there. Okay, back to code. See if we can figure this out. Let me see if we can do that. Okay, that didn't change anything. I didn't expect it to. Okay, let's make sure our timers are set to the same. So timer 7. double check our values of these timers. So timer 6 is the toggling rate. Timer 7 is the simulation rate. Okay, so I do have a difference here in the simulation rate. So let's change this. So 0 prescaler is going to make this run at, this is basically going to make the timer run at 1 millisecond, which is, I'm not quite sure why, but let's run this and see what happens. Okay, getting closer. I think there's a timer issue here, so it's when it's calculating the RPMs. I think there's something that's off. So now it looks like it's off by about a factor of 2. So let me try to figure this out. I'm going to pause real quick. Okay, found one issue. We're not updating p old here, so we're using p old, but it's really staying at 0, right? So we really need to say p old equals p. So the next time we iterate, we'll actually have that previous value. So it's not actually operating on the previous value, it was operating on just a constant p old. So let's see if that helps. Okay, well, we are going to the commanded value, but now we have some pretty large instability. So we are closed loop. You can see these oscillations are around the commanded value, but obviously we've got some issues here on the control system. So if we were to go down to 0 to say 2, you'd see, let's go like -5 to 5. You can see now, yeah, the p-value is obviously very high, and the error is pretty high as well. Okay, so let's see if we can figure out what's going on there. Again, you know, sometimes these things don't always work right off the bat. You kind of have to, you know, do a little troubleshooting, see if you can figure out what the problem is. So I'm going to stop this motor. It's going a little crazy. Okay. Let's see what the problem could be here. We are updating P. The pulse value, we're not really looking at what that is, but I think that should be fine. Well, yeah, let's take a look at pulse. So let's do %LD. So let's see what our pulse value actually is. Maybe that'll shed some light to make sure that it looks appropriate. So I'm going to restart this. Sometimes you got to restart this to kind of clear out the number of variables it's finding. Okay, so we just look at pulse. It's kind of over on the far right. Let's go up to 15,000. Okay, you can see the pulse value is trying to go pretty high. We obviously can't command anything that's over 10,000, right? So it could be that the control system is really, this is kind of one of the non-linear aspects I was talking about. You know, it's trying to command a pulse value of over 10,000. which can cause an issue. In this case, it just kind of limits it out. So I don't know if that's really the problem here, but you know, that's something you could limit in the code just to make sure that you don't have any issues. So we could go ahead and do that just to make sure that doesn't cause any problems. So after we calculate this pulse, let's just put in some error checking to say if pulse is greater than 9999, we'll make it equal to 9999. Else, if it's less than 0, we'll make it equal to 0. So we're kind of limiting that pulse value. It's already an unsigned value, so we don't really need to lower it. Look at the minimum, but I'm going to go ahead and do it just for grins. Okay, so that's limiting that. Now I think one other thing here is we're using error old here, and we're not updating that as well. So let's update that. So error old equals error. So don't forget to update your you know, these states, because you gotta have to use those for the next iteration. So that's, I think, what's going on with this guy. So let's try it now. I'm gonna restart this. Okay, motor definitely sounds better, right? Okay, let's go from 0 to 250. Ah, yeah, okay. So we don't need to look at the pulse value, but here you can see the red is the command and yellow is our actual response. Okay, so I think that looks pretty good. It looks like it's reaching our exact. If you look over here, the measured value is kind of right beside it, so it's going, you know, it's hard to see with the dithering, but you know, looking on the plot, you can see it is actually really kind of, you know, converging on that commanded value. So we're commanding 100 to 200, and the motor is actually reaching those pretty quickly, no overshoot, and pretty quick response, right? Okay, so let's just compare that to what we would predict with our simulation. So let's code in, you know, the output of the motor if we just kind of use our state space representation of the motor and driver, and just see mathematically if that kind of looks like what we would expect. Okay. So I'm going to make this. Okay, that looks correct. Okay, so let's make a new variable called sim out. Let's start a new line here. Float sim out and sim out hold. So that's going to hold the old value of our output, right? So, you know, our motor is going to be, the transfer function is going to be a function of the output, you know, and the old output. Okay, so again, this is kind of back from our simulation of the motor itself. So we have these parameters as well. So let's put in the state space simulation of that. I'll go ahead and say simulation of closed loop system. Okay, and so in this case, we're going to have sim out is equal to sim out hold. And this is the simulation we did before, TS times minus 1 over Tm. This is the state space representation. So this is going to be like our integral estimation, right? Our kind of our x dot, or x is equal to old x plus, you know, this simulation time times our x dot. So this will be times sim out get away from me. Sim out old, and then plus kg times, I'm sorry, kg over tm times p. Okay, so we're still using the same control, but this is just kind of going to give us what we would expect the motor response to be, you know, kind of given that control. Okay, and then we'll update sim out old equals sim out. Okay, so the simulation out should give us mathematically the response of the motor and driver to this control signal P, right? So that just gives us something to kind of plot and you know, and see if it looks you know, relatively the same. Okay, so I'm going to put that right beside rate. I'm going to say sim out here. So we'll put another float output here. Okay. So let's see if that compiles. And let's run that. And I'm going to start this over again. Let's go from 0 to 250. Okay. And that's our simulated output, which, you know, doesn't really look the same. And I'm not sure why. Let me take a look. That looks more like an open loop output. It's a little slow, doesn't it? Okay, so let's look at our simulation. Function of the motor response. We have kg over tm. Okay, that all looks reasonable. And we have our kg and our tm defined. So, you know, because this is a mathematical simulation, it's not actually closing the loop on this system. So the relative, you know, height of these is kind of open loop, right? It really depends on this kg value, how accurate that is, you know, as a function of this p. So sometimes you'll get, you know, a little bit of a level difference, but it does look like it's a little bit slower ramp up. If you were to kind of line those up, you'd see this is really going pretty fast. I'm going to go ahead and implement the open loop version and kind of see what that looks like as well. So let's simulate the open loop system. So this would be the motor response to just the command, and not to the control system output. So this should show us the slow rise time that we would get without control. Okay, so let's create some new variables here. Open loop and open loop old. And let's implement those. And those are going to be the same, so let's go ahead and just copy and paste that. Make this quicker. We'll make this open loop is going to be open loop old, open loop old. Instead of reacting to P, we're going to react to command. But we don't want this kg factor in there, right? Because that's, command is already an RPM. So this needs to be kind of command divided by kg, right? Or we're going to have RPM, you know, factor in there twice. So let's just take out that kg. And then this is the open loop. Hold equals open loop. Okay, and we'll do open loop as another output here. So let's see what those both look like. To 250. Okay, so the open loop output is that gray. I'm going to get rid of the pulse value and the error. Okay, so now we're really just looking at, you know, our simulated open loop. That does look, actually looks correct, right? So the reaction to the command is causing that to be, the gray is the open loop, basically. So that's how the motor would look without a control system. Okay, so we could test that out and make our motor, our physical motor, respond to the command and not the control system output, the controller output. And that would be something that we'd expect that to kind of match, right? So let's do that real quick and see if that does look correct. So let's take our pulse. Let's see, how do we want to do that? So instead of this pulse being equal to a function of p, let's just temporarily change that and make that equal to times command, which again is it's in RPMs. So we want that to be something between 0 and 1. So I'm going to divide by kg here, just so that command is now more like percentage of max RPM, if you get my drift. Okay, so now we're not closing the loop with the control system. We're just making toggling the pulse value up and down, and it's going to cause that motor and driver just to operate open loop. So let's see what that looks like. Okay, so again, the levels are a little bit off, right? Because it is open loop, it's not closing the loop. But here you can see that, yeah, it looks pretty close to the response that we're getting. The simulated response here is a little slower, right? For some reason, it looks like our model is a little bit slower than maybe actuality. But you can see it's kind of the same. The motor is now not being driven by the control system, so you can see its response is a little bit slower to reach these values. You know, we could try to line these up mathematically by playing with some of these conversion factors of duty cycle to RPM. But the main thing here is just kind of look at the general shape. Okay. All right, so let's. And you know, you can see it's not closing the loop, so it's really not reaching the commanded values. We're supposed to be going from 100 to 200, but we're going from, you know, 130 to 250 or something like that. So, you know, again, the control system is not active right now. It's just open loop. And you can kind of see that response is slower. So if we go back in here and re-enable this control system, you know, we can see that now it'll be using that controller output as the driver of the PWM, and that should cause it to, you know, have the fast closed loop response time. So again, the gray is kind of the open loop response. Yellow here is with the control system. So you can see our control system is actually causing our rise time to be much, much faster. We're reaching our desired value, much quicker than the original, response time of that motor. Okay, so let's figure out why our simulated response is a little different. Which one was that? I'm going to start this over. These. And you can see here the orange. It looks actually pretty good for the bottom here, right? Except for being a little bit off in magnitude. That's interesting. There's kind of a strange rise time at when it's going up, but when it's on the downside, it's actually pretty squared off. It looks a lot like the actual. So I'm not sure why that is. It could be maybe because that nonlinearity issue with p, right? So if our p value is trying to go higher than 1, it's not. Oh, it is trying to go less than 1. So that could be one reason why that's happening. It's kind of limiting that, because whenever this p goes down below 0, the duty cycle isn't going to go below 0, right? It's going to go down to 0. So, we might need to kind of change the gain of our system so that this isn't happening, because that's really going to be kind of useless, right? P isn't going to actually be able to affect the system that far. So let's kind of change our gain and see what happens. Let's say we make this now like 1. Let's see what happens. Again, this is the output of the control, which is what the system is actually responding to. Okay, so now you can see that p value is staying within 0 to 1, so I would expect that this would be more representative of what the simulation would show, but let's go take a look. Okay, so yeah, so now you can see the rise time is really, mimicking. There's a little bit of oscillation, a little bit of overshoot, right? So that's, what we would see. I can get rid of the, we could, add a factor here to the simulated output to make these match a little better. In fact, it's off by about, I don't know, it needs to be multiplied by maybe 30%. So if we did like a 1.3 factor on that output, it might let's see, what if we did 1.3 times kg? I'm just kind of experimenting here. This may have an undesirable effect, but just trying to kind of get those graphs to line up a little better. And the reason it's a different value is we're actually closing the loop based on, the yellow output. The orange isn't really driving back into the controller, so it really is kind of an open loop. But here you can kind of see it's a little bit closer aligned. We can kind of see that comparison of that response. But the main thing is, you do see a little bit of overshoot in the orange, right there, which is actually the same response we're seeing in the yellow. Same with the downside, maybe a little bit of overshoot in the downside, and the yellow is as well. So, we could probably tweak a few things and get that response to be a little better. We could maybe, remove that overshoot. I know that if you, increase KP, you can remove that overshoot, but then we kind of run into the, maybe, running into the limits of P itself. You know, maybe you could reduce the KI. Let's see what happens there. And, you know, you could do all this in MATLAB too, to kind of use that as an environment to play with some of these values. Okay, that actually didn't help much, right? So that really causes the response to be really slow. So that it definitely got rid of the overshoot, but you know, now we have a much slower response time. But you know, at least the simulation is kind of showing the same thing as the actual, so that gives me confidence. And it's still a little bit faster than open loop, but this is obviously something we wouldn't want to, a condition we wouldn't want to operate in. Let's change this to 1.5, see if we can kind of get a happy medium between the simulations. Okay, so again, you know, kind of a part way between. You know, again, the upper side is kind of getting clipped, and I think that's because of the the range of P. So you kind of have to, you know, the simulation is a little different from reality just because the simulation doesn't have the non-linearity aspect added in there. So take that with a grain of salt, but you know, I think we've seen that in general that the simulation is kind of matching the output under most conditions. Okay. All right. So basically, in essence, what we have here is red is the command, yellow is the actual motor response, and the gray is what the motor would be doing without the control system. So basically, this just shows you that the controller is actually causing a much faster response to reach the command. We're using a PI controller in this case, so we're reaching our final value exactly, and we're reaching it quickly. So this is a really good controller for this particular motor. You know, there's no, with these parameters, there's no overshoot and a very, very fast response time. So that's really the purpose of this. So hopefully this was helpful. I think you can see there's a lot to this. You know, you really have to think of a lot of different things on these implementations, like, you know, whether you're operating in the domain of RPM, you know, 0 to max RPM or 0 to 1 as a duty factor percentage. You have to make sure you kind of account for that in your simulation, in your implementation. So for our implementation, you know, we're basically creating an error which is between 0 and 1, between 0 and max RPM. Equivalent to the 0 and max RPM, we're creating an error that's between 0 and 1, and so therefore P is going to be basically based on that error. So P is going to be a duty cycle between 0 and 1. And then, you know, when we actually go to calculate the pulse, now we're calculating a pulse between 0 and max pulse value. So everything's kind of in normalized, you know, but then when it comes to actually you know, calculating that error, that's where we have to, the value coming back from the motor is not going to be between 0 and 1. It's going to be an actual RPM value. So the error, we're basically doing that normalization at this step. But everything else is in kind of a, you know, a 0 to 1 type thing. So when we look at command and rate, those are both in RPM land, but everything else is kind of in a 0 to 1. So this is, you know, command and RPM rate, and the gray, of course, is simulated. But if we go to that, you know, down in the plus and minus 2 range, you know, you can kind of see we have our error, which is channel 4, and then we can see our P value between 0 and 1, you know, is that green. So a couple of different ranges to kind of think about, and you know, in this case the translation between the two is the motor's, you know, RPM per duty cycle factor, which is essentially our kg value that we derived, right? So for a 100% duty cycle, we get, kg is our RPM rate. So that rate, that number, that conversion rate is not constant. If we were to look at that across the values of duty cycle, we would see that changing. But I think, for now we can kind of estimate it as that one value, and then, convert from there. But since this is a closed loop system, it's going to reach, that desired commanded value, right? That ki part of the controller is going to cause an error when you're not exactly equal to your commanded value. So that helps close that loop and get you exactly to your commanded value, even if that conversion rate is a little bit off, Okay, so hopefully this helps. This is, I know, a pretty long video, but it's a lot of stuff to cover for actually how to do the actual implementation of a control system in an embedded controller and all that goes into it. Lots of things to think about. So I want to give you guys a good example of this. Okay, thanks.